This module is about reducing project duration. There can be several reasons why one might want to complete the project early by reducing the duration of one or more activities in the critical path. Early completion of the project would imply early realization of revenues and/or a reduction in indirect or overhead costs associated with the project. Some of the other reasons for reducing the duration of a project may include customer requirements, contract commitments, time to market pressures, bonus for early completion, pressure to move resources to other projects, etc. But the reduction in the duration of some of the activities would typically imply more direct cost than the cost for the normal duration of the activity. So one has to balance between the benefits of completing the project early with the increased direct cost of completing the activities. There are several possible alternatives for reducing the completion time of the project. These include adding additional resources for some activities, scheduling overtime, outsourcing some project work, forming a competent, dedicated and focused core project team, adopting a critical chain approach to project management, etc. Now we will consider the problem of reducing some of the activity durations in order to complete the project early. In order to reduce the duration of an activity from its normal time, we have to incur incremental direct costs consisting of perhaps overtime payment and/or cost of additional resources. The relationship between the incremental direct cost and the reduction in activity time is assumed to be linear as shown in the diagram. For each activity whose duration can be reduced, we need to estimate the incremental direct cost for each unit reduction in duration. For each activity, there would be a minimum required time beyond which the activity time cannot be reduced. The minimum time and the corresponding direct cost are often referred to as crash time and crash cost. The slope of the line in the diagram gives the incremental direct cost for each unit reduction in the duration of the activity. We can, if necessary, consider certain type of nonlinear relationships between the reduction in the activity duration and the increase in direct cost, but we will not do so in this module. Let's now consider the same software project example that we used for drawing the network and calculated the early start and late start of each activity. The table shows the normal time and the associated normal direct cost, as well as the crash time and the associated crash cost. From this, we can calculate, as shown in the table, for each activity, the maximum possible reduction from the normal duration and the slope of the assumed linear relationship. Recall that with normal duration for each activity, the project completion time is 11 weeks. The critical path is shown in red in the diagram. Now suppose there is a bonus of 40 in thousands for each duration in project completion time by 1 week. Hence, we want the least incremental cost for reducing the project completion time by 1 week. Clearly, the project completion time can be reduced only if we reduce the duration of the activity on the critical path, which is activities A, B, E, F, G, H. In this critical path, the duration of only activities B and E can be reduced. For activity B, the incremental cost of reducing the duration by 1 unit is 25, while the incremental cost of reducing the duration of activity E is 30. Hence, it is better to reduce the duration of activity B. Since the bonus is 40 for 1 week reduction in project completion time, we reduce the duration of the activity B by 1 unit. That is, the duration of activity B is reduced from 4 weeks to 3 weeks, incurring an incremental cost of 25 while getting a bonus of 40, thereby having a net gain of 40 minus 25 equal to 15. Now the project completion time is 10 weeks. We now have two critical paths as shown in red in the diagram. In order to reduce the project completion time further, we need to reduce the length of each of the paths A, B, E, F, G, H and A, C, E, F, G, H. Now we have to consider two possibilities. One in which the duration of the activity that is common to both the paths is reduced by 1 unit, and the other in which we reduce the duration of two distinct activities, one in each path, where each activity is in one and only one of the two critical paths. In this example, activity E is on both the critical paths, and the incremental cost of reducing its duration by 1 week is 30. The other possibility is reduce the duration of both activities B and C, incurring an incremental direct cost of 25 plus 25, which is 50. Since 30 is less than 50 and 30 is less than the bonus of 40, we reduce the duration of E by 1 week, that is from 2 weeks to 1 week, thereby having a net gain of 40 minus 30 equals 10. Now the project completion time is 9 weeks. We still have the same two critical paths. Now since all activities except B and C are at their minimum crash duration, the only possibility is to reduce the duration of both the activities by 1 week. This, however, implies that the increase in direct cost would be 50, whereas the bonus is only 40. Hence, we would not reduce the duration of activities B and C. Note that if the bonus was 50 per week, we would reduce the duration of activities B and C by 1 unit, and the project completion time would be 8 weeks. No further reduction in project completion time is possible since all the activities on the critical path are at their minimum duration. Note that if all the activities on any one of the critical paths are at their minimum duration, the project completion time cannot be decreased any further. It should be noted that as we keep reducing the activity durations, more paths become critical and more activities are on one or more critical paths. The critical activities must be managed well so that none of them take a longer time than the stipulated duration if the project completion time is not to be delayed. So reducing the project completion time typically implies that the flexibility is lost and project management becomes more difficult. The above approach to reducing the project duration is conceptually sound, but for large problems it becomes very cumbersome and difficult to implement. A linear programming approach to solving this problem would be most appropriate. This completes this module.